These are the notes for section 6.4 in your textbook. First, we need to define a new term, and that is compound statements. Compound means we're putting two things together. We're going to work with two different kinds of compound statements. The first are and statements. This is where we take two statements and we join them together with the word and. Here are some non-mathematical examples. In and statements, two things have to both be true at once. For example, it's Tuesday and the sun is shining. For this compound statement to be true, two things have to be true. It has to be Tuesday, not any other day of the week, and at the same time the sun must also be shining. If it's Monday, then the statement is false. If it's cloudy, then the statement is false. Both things have to be true at once for the whole compound and statement to be true. In math, we'll have statements that look like this. X is greater than 2 and less than 4. This means that I'm looking for numbers for x that are both greater than 2, 2.5, 3, 3.5, etc., and that are less than 4. Both of those conditions have to be met at once for the whole compound and statement to be true. The second kind of compound statement that we'll work with is called an or statement. This is where we have two things and either one or the other has to be true, but they're not required to both be true at the same time. For example, it's Tuesday or the sun is shining. This statement would be true on a sunny Monday, and it would be true on a cloudy Tuesday, because in both examples, one part or the other of the condition is met. If it's Tuesday, it doesn't matter what the weather is like. The statement is true simply because it's Tuesday. If it's sunny, it doesn't matter what day of the week it is, because the condition that the sun is shining has been met. For an or statement, only one or the other of the things has to be true for the overall statement to be considered true. In math, we'll look at statements like this. X is greater than 1 or less than -1. Any values for x that meet either condition, numbers bigger than 1 or less than -1, will make this whole statement true. First, let's look at some of these compound inequalities. We're going to work with the or statements first. So here's a statement, x is less than -1 or x is greater than 1. This is really a compound inequality. It's two separate inequalities that we've kind of smushed together. The first one is x is less than -1. We can show that using the inequality boxed in red. The second one is x is greater than 1. We can show that boxed in blue. So one or the other of these has to be true. Notice that there's no value of x that makes them both true. This may be a little bit easier to see if we put these two inequalities on a number line. So here's a number line. First, let's show all the numbers that are less than -1. So highlighted in red here is everything less than -1. And since -1 itself is not a solution to this inequality, I put an open circle over the -1. Now I'll show the other inequality in blue. X is greater than 1. So here's everything greater than 1. And x could not be 1 itself. So there's an open blue circle over the number 1. Solutions to the compound inequality are any numbers that are shaded over in either color. All I have to do is pick a number that's either shaded over in red, that makes the first inequality true, or that's shaded over in blue, that makes the second inequality true. Notice that there are some numbers in the middle there, for example 0, that don't make either inequality true. So the solutions to this compound inequality are all the numbers on the number line that are shaded over in either color. When we have compound inequalities that are joined with the word and, you'll sometimes see them as though there's a variable in the middle of two inequality symbols. In this case, again, what we really have is two inequalities that are joined together with an and. The first inequality is 1 is less than x. Another way of saying this is that x has to be bigger than 1. Notice that x is on the greater side of this inequality. So there's the first one. And at the same time, it also has to be true that x is less than 5. There's really two inequalities there, even though we only wrote the variable once. X has to be greater than 1 and also less than 5. Another way of thinking of it is that this means x has to be between 1 and 5. Let's picture this on a number line. First, we'll graph x is greater than 1. So here, shaded over in blue, these are all the numbers where x is bigger than 1. And we also need it to be true that x is less than 5. So shown here in red are all the numbers that are less than 5. I need the region where both of these two statements are true at the same time. That's the region that's shaded over in blue and in red. It's that stretch in between 1 and 5, where both statements are true at once. That overlap is where x is greater than 1 and less than 5. Any number in that region, 2, 2.5, 3, 4.168, will be a solution to the compound inequality. How do we graph that compound inequality? Well, we would show the number line, and we would only show the portion where the red and the blue overlap. We would show that segment there. Notice that both 1 and 5 have open circles over them, indicating that neither 1 nor 5 are solutions to this equation, but everything in between them is. It is possible to write an inequality that has an infinite number of solutions. For example, x is less than 2 or x is greater than 1. If we graph these two inequalities on a number line, you'll see that x is less than 2 is shaded over in red, and x is greater than 1 is shaded over in blue. And when we do that, we have effectively shaded over the entire number line. No matter what number we pick, it's either less than 2 or bigger than 1. So x could be any real number. There are also inequalities that have no solution. For example, x is greater than 7 and x is less than 5. If I graph those two inequalities, I'm looking for the overlap region because this is an and statement. I need both statements to be true at once. And notice that there is no overlap here. There is no number that is both smaller than 5 and bigger than 7. If you think about it for a minute, that statement makes tons of sense. A number can't be smaller than 5 and bigger than 7 at the same time. So how do we work with and solve these kinds of inequalities? Let's start with solving compound inequalities. When we say solving here, what I'm trying to do is to get the variable, the x in this case, all by itself so that I can see what values it's okay to plug in for x. So I'm trying to get the x by itself here. Step 1 is we want to get the variable term, that's in this case the 2x, by itself. In the past, we talked about adding and subtracting the same thing to both sides of an equation or an inequality. In this case, this inequality has 3 segments, and so we need to subtract the same thing from all 3 segments there. Then we want to get the variable all by itself. Right now we have 2x in the middle. To get the x by itself, we need to divide by 2. And to make sure that we don't mess up our inequality, we need to divide everything by 2. We're dividing by a positive number, so we don't need to flip any inequality signs around. And when we do that, we get that x is between 2.5 and 5. This is another way of saying that x is greater than 2.5 and x is less than 5. Remember, instead of doing the same thing to both sides of the equation or inequality, you're doing the same thing to all three sections of the inequality. To simplify compound or inequalities, what we're going to need to do is to work through each statement separately and just leave the word or joining the two together. So here's an example. 2x plus 3 is less than 9, or 3x minus 6 is greater than 12. And I want to know what values of x make one or the other of these two statements true. So first, I'm just going to work with the inequality on the left. I'm going to subtract 3 from both sides to get 2x is less than 6, and then I'm going to divide both sides by 2 to get x is less than 3. Now I've solved that inequality on the left, and I know that any number less than 3 will make that one true. Now I have to look at the inequality on the right. I'm going to add 6 to both sides, and I get 3x is greater than 18. When I divide both sides by 3, I get x is greater than 6. So in order for the original compound OR statement to be true, one or the other of these simplified conditions has to be met. Either x has to be less than 3, or x has to be greater than 6. Any numbers less than 3 will make the left-hand inequality true. Any numbers greater than 6 will make the right-hand inequality true. If I graph these on a number line, I'll show x is less than 3 in red, and x is greater than 6 in blue. Any number that's shaded over by either red or blue will make one or the other of the inequalities above be true. This is the end of section 6.4. These concepts of solving less than and greater than inequalities that are joined by the words and or will become very important when we do section 6.5, which is one of the hardest sections we do all year. 6.5 and 6.6 are real doozies. So please, if you're feeling shaky on this, go back and review your notes and make sure that you've got a really solid understanding of this.